Okay, we are going to focus on 3 rules today. We're going to look at the product rule, we're going to look at the quotient rule, and then we're going to look at sum and difference. We're going to group together because those aren't done any differently. Now, each of our rules today have the same index. Remember, index is the little number in the corner of that radical. If we do not have the same index, then these 3 rules do not apply. We don't have a way to do any of this if those indices are not the same. Yet. Keyword yet. No. It's next week. We will get to a way we can do it if the index are not the same. But for right now, all 3 of these rules are contingent on the fact that that index in both problems or all parts of the problem are the same. Good? Okay. Product rule. This says that the nth root of A times the nth root of B. I don't actually care what A and B are. They could have the same variables, they could be different variables, one could be a number, one could be variables, it doesn't matter. If my indices are the same, they both are the nth root, then I can go back and forth between this expression, the nth root of A times the nth root of B, and the expression, the nth root of A times B underneath the radical. So I can either have all of my I can have all of my expression under one radical, or I can separate it. Well, we've actually already done this. The last 2 problems that we did on the homework that we just looked at, we separated it and said, okay, what would it look like if I pulled apart just the numbers or I pulled apart just the variables? That's okay to do. That's the product rule of radicals. So here's what that means. When I multiply radicals, I can combine everything that's inside the radical, and I can combine everything that's outside of the radical, as long as the indices, the index of each are the same. So if we look at this first example, and I notice I'm going to zoom in, I notice my index on both of those. What is the index, even if it's not written? 2. These both have the same index. Okay? So because they both have the same index, I can rewrite this as 5 times 2, and then the square root I can do 3 times 15. Now probably I would just do that math in my head without writing it down like this. I wouldn't show this step. So I can write this as 10 root 45. Now, unfortunately, this is not our final answer. Oh, why? Because there are situations where we will come up with something that now needs to be simplified. And I can simplify the square root of 45. Why? What is a perfect square that goes into 45? 9. I know that this is 10 root 9 times 5, and I happen to know what the square root of 9 is. What is the square root of 9? 3. So I really have 10 times 3 root 5, or 30 root 5. It's not that bad. It's just combining by multiplication. Questions on that? Well, let's look at the next example. Cube root of 6 times square root of 2. I want to multiply. Why? They're not the same. What's not the same? This index and this index are not the same. These indices are not the same. I have a cube root. I have a square root. I can do nothing with this problem yet. Yet. It's not possible yet. Yet. Keep that growth mindset. We can do this. Okay, let's look at what it looks like when we have variables. Because it does get a little bit messier, but really the process is the same. First thing I want to do, check to make sure my indices match. Can I multiply these? Yeah. Really, when I multiply these, I get 2 times 6 and x to the 5th times x to the 8th, which would give me root 12 x to the 13th.
Is that 2 times 6 times x to the 8th?
Yeah. It's all multiplied. So I get 12x to the 13th. Can that be simplified? Yes. What perfect squares go into 12? Let's start with the 12. 4 and 3. So this is the same thing as the square root of 4 times the square root of 3. I know the square root of 4. What is it? 2. Okay, let's look at the x's as well. X to the 13th. I'm looking to break them up into groups of how many? 2, because the index is 2. How many groups can I get? Well, I've got an x squared, x squared, x squared. I'm up to x to the 6th, 8th, 10th, 12th. Oops, probably didn't want to write 12. 12, and then just an x that's left. Count them to make sure. This is 2, 4, 6, 8, 10, 12, 13 x's. How many x's are perfect squares? 1, 2, 3, 4, 5, 6. So I should have 6 x's outside, otherwise known as 2x to the 6th. I probably would just write it that way. Now I'm going to write what's left over. Well, what's left over? 3x. So my final answer to this would be 2x to the 6th root 3x. Not so bad, right? Let's try the next one. You try the next one. So let's go over this one. What did we get when we first multiplied them together?
72x4 divided by 5.
You guys agree? 72. How would you break down 72 so that you had the biggest perfect square in there? 36 and 2. We would do that because we know the square root of 36 is what?
It's got to be 6.
6. All right. Let's focus on the variables now. X to the 4th. How could I break that into perfect squares? X squared, which means that what comes out is an x and an x. Because the square root of x squared is x, the square root of x squared is x. That comes out. What about the y to the 5th? And then y. Right, so we have a y that comes out, and one that's inside. So what's left inside is a 2 and a y. What's outside is a 6x squared, y squared. How'd we do? Ready to try cube? Try cube. You can do it. Notice I kept the indices the same this time. Multiplying these together, we add the exponents. The index doesn't change. It's just x to the 7th times x squared, which is x to the 9th. How do I simplify that?
You take out all x cubed.
Right, because I'm looking for groups of 3. And x to the 9th could be rewritten as x cubed times x cubed times x cubed. You do not have to write this out as x cubed times x cubed times x cubed if you understand that this is 3 groups of 3. That's fine. You don't have to do that. But I know this is a perfect cube, this is a perfect cube, this is a perfect cube. Leaving me with x times x times x, or x to the 3rd.
That's fast.
See, it's not so bad, right?
No, this is easy.
Okay. Let's move on to the second rule, which is the quotient rule. And what does quotient mean? Answer to a division problem. Okay, so let's look at the quotient rule of radicals. Just like with the product rule, the first thing that we need to verify is that the indices are the same. I cannot simplify this unless those indices are the same. Now, I'm going to tell you that the quotient rule is not always best done by combining them, like I'm about to do. Sometimes we actually want to separate them, and it makes their life easier. So, the quotient rule says this. I could rewrite this whole thing to be the nth root of a divided by b, meaning I can stick it all under one radical. But I can go in reverse. These two rules are what we call biconditional. I can do it this way, or I can separate it, or I can start in the separated form and combine it. It's biconditional. Sometimes it's beneficial to combine them first, because when I combine them first, then I simplify, and it makes my life easier. You could simplify first, then combine, but there's a very strong chance you'll have to simplify again. Same is true with multiplication. For example, if I go back up here, just watch, because I wouldn't actually do it this way. If I go back up here and I were to simplify 2x to the 5th and then 6x to the 8th first, watch. I know x to the 5th is x squared on the outside and an x on the inside. X to the 8th is x to the 4th on the outside and a 6, no x's on the inside. I could simplify those first, and then I could combine them. So we'd get x to the 6th on the outside, square root of 12x, but then the problem is I now have to simplify again. So sometimes it doesn't benefit to simplify first, especially in radicals, because you end up having to simplify again. I would have to simplify this root 12. And that's why I wouldn't simplify first. I'd multiply. Same is true with division. Okay? Here's what I mean by that. First thing I want to do is I want to check to make sure that my indices are the same. Are my indices the same? Yes. They're both 2. I'm good. Now what I'm going to do is I'm going to rewrite this as one radical. Square root of 18x to the 5th over 2x cubed. The beauty of this is that simplifies. Why? 18 divided by 2 I can start with, which is just 9. And what is x to the 5th divided by x cubed? X to the 2nd. Very good. Do you guys want a quick review? Do you want a quick review on your exponent properties?
Just, like,
Yeah, give me a little
subtracting 5 minus 3.
Yeah, great. Let's do a quick review. And yes, you are correct. I'm
X to the 2.
going to write them right here because I don't know where else to put them.
Would that be right?
No, we're not done. We got to simplify.
It's not gonna simple now. I know, but I always wish it. What are you writing down right now?
3x.
Okay.
Just 3a.
If my bases are the same with exponents, remember we add the exponents. We leave the base alone. Remember, if my bases are the same and I'm dividing the exponents, we leave the base alone and we subtract the exponents. Do you remember doing that? And if the bases, well, if there's only one base and they are raised to another power, this is when we multiply the exponents. Do you remember those rules? Now you do.
What's that bottom one?
If we have a power, so if I have a base and an exponent, but that's raised to another power, then we multiply.
Gotcha.
Good? Okay, there's our quick review. All right, am I done with this problem that we started? No, why? I can simplify it. Do I know the square root of 9? Do I know the square root of x squared? So my answer would be 3x. We are going to assume all of these are positive. So I don't need the absolute value. Unless it says something. For example, if this had an absolute value, I would put absolute value around just the x because 3 can't be negative. Because it was an even root. Remember, even roots, so square root, fourth root, sixth root, they have absolute value. I don't need that, so I'm going to go ahead and erase it. All right, you try a fun one. Yes!
Show.
Love fun ones.
Let's talk through it. So we have the 3 and
First thing I want to do is divide these. Because the indices are the same, I can go ahead and divide that. But that's the first thing we want to check. Make sure these index are the same. If they're not, I'm done as of now. Next week we'll change that up a little bit, but for now I'm done. They're the same. So I can rewrite this as one big fraction. Do you need to write this out? No, you really don't. If you can see the division and you go ahead and comfortable to do the division, that's fine, you guys. That's fine. Skip this step. What is 162 divided by 3? 54. So don't lose the index. This is the cube root of 54. Y to the what power? Third. Great. Do I have a cube root of 54?
Yes.
Yes. Well, I will. What perfect cube goes into 54? 27 and 2. So the cube root of 27 times 2y to the third. This is a perfect cube. The cube root of 27 is what?
3.
But y to the third is also a perfect cube. What's the cube root of y to the third? Y. What I have left is the cube root of 2. Remember, we talked about it's important to keep that index. Make sure you still have that index of 3 written there. So 3y cube root of 2. How do we do? Good.
We were close. We were getting there.
Great. I like getting
I
there.
have a question. Will we
Yes.
have like a little chart with all the cubes and the squares?
I'll give you something along those lines, yeah.
Okay.
I have one. It's already printed out.
Okay, awesome.
I have my other notes with me right now. I'm over here like,
Keep those out. That's totally fine. Keep those notes with the perfect cubes. All right.
yeah, I think so.
Problem is,
Yeah. The problem is.
are we ready?
Yes.
All right. The problem is, if I have a square root in only the denominator, we have a problem. It's considered bad math to have a square root in the denominator. It's like saying I is hungry. We all know what you mean, but it's considered wrong. You ready for the worst double standard ever, though?
Yes.
It's only wrong until you take your SAT, ACT. After that, like in calculus, guess what we do? We leave the square root in the denominator. Yay! But you cannot. You are not there yet. But after this year, you will be there. You will not have to change it. So, in any case, for now it's considered wrong. It is wrong. And let's talk about why. Okay. Back when math was invented, I know this is shocking to you, there were not calculators.
Oh no.
Right? So, when they tried to figure out the division, 1 divided by root 2. Well, what is root 2? Well, root 2 is a number that's a crazy decimal. 1 point something, and it's long. It's really hard to do 1 divided by that crazy decimal. But if we go through the process of rationalizing the denominator, or multiplying by a magic 1, it's much easier to multiply by decimals than it is to divide by decimals. So way back when we didn't have calculators, and sadly it wasn't even that long ago, it was not okay to have a division by a decimal. It was okay to have a multiplication by a decimal. The square root of 2 would be a decimal. So that's why we rationalize the denominator. It makes it easier to estimate in our head what the answer would be than it would be with division. That's the answer. Okay. How many of you have heard of the process rationalizing the denominator?
I think so.
Yes. Okay. Oops, I missed the end. Totally missed the end. Didn't even come close. We're just going to go ahead and box. Rationalize the denominator. Some of your teachers may have called this the magic 1. Okay. Here's why. What happens when I multiply a number by 1? It's the same. It's itself. Right? So if I can multiply a number by 1, I'm not actually changing the problem, am I? Now, the reason this is called a magic 1 is because we're going to make it so we multiply by the number 1, but it's not going to look like 1. The process of rationalizing the denominator is to take the radical that is in the denominator and multiply both the top and the bottom by that number. Okay? The square root of 2 divided by the square root of 2 is really the number 1. Why? It's divided by itself. Root 2 divided by root 2 is 1.
That was clever.
I've done that before.
Yeah. So clever. I'm really just multiplying by 1, but watch what happens. When I multiply straight across, we get root 2 on the top, and we get the square root of 4 on the bottom. But what is the square root of 4?
2.
So I get root 2 over 2. I have rationalized the denominator. This is easier to do. This is the answer. My square root is now in the numerator, not in the denominator. Because I can take a crazy decimal and divide by a whole number much easier than I can take a whole number and divide by a crazy decimal.
So it's okay if it's on the top.
It's okay that it's on the top. It's not okay that it's only on the bottom. Because of the division. Division, that's what I was just telling you. It's easier to divide by a whole number than it is to divide by a decimal. In your head, when we didn't have calculators.
So we would just leave it like that?
Leave it like that.
Will we have to simplify it?
If it needs simplified, yes, you will need to simplify more.
Let's do the next one.
Let's do the next one. You try it.
No.
You got it. Try the next one.
Okay, so 5 over
All right, on this one, what would be your magic 1?
8x
Root 8x. Okay, I'm just going to write it right here. Root 8x.
over 8x.
Root 8x. So in the numerator, what do I get? 5 root 8x. There's really nothing else I can do. In the denominator, when I multiply those two, what do I get? Root 64x squared, which simplifies to what? 8x. Okay? Say that again.
Oh, never mind. Sorry.
Okay. Now, does the square root of 8x need simplified?
Yes.
Yes.
Ooh.
I know that I can take a 4, 4 times 2 is root 8x. So I know that this, the square root of 4, I know that that's 2.
10 root 2.
Which is 10 root 2x over 8x. Now, this answer is correct. This is almost 100% correct. I can simplify. I have the fraction of 10 over 8.
That's 5 over 4.
I know that 2 goes into both of those, so it'd be 5 root 2x over 4x. Now, let's talk about this. Am I going to accept this answer? Yes. Is Math Excel? No. On the SAT, will this answer be there?
Yes.
No.
But it
This
would
will
be
be.
wrong.
This is not wrong. This is not wrong. This is a better answer. Now, the good news is they won't give you both and say which one is the best answer. They're just going to say
which one's ready.
there's going to be one answer that's correct. I am guessing, however, that 99% of the time, if you get to this point, it will be no challenge for you to go, oh yeah, that's the answer. That makes sense. Because you already have those answers listed there, right? It's easy to see this and say, oh, I understand why that's the answer. It's hard to get to this 10 root 2x over 8x. Can you get there? If you can get there, you're doing well. Ready to make it a little more fun?
No. Always.
No, I actually.
Well, I got one more example of these.
This is crazy.
Now, we're going to go over this one. Here's the problem with this third one. What's the index? 3. So if I want to get rid of the cube root in the denominator, I need something that's a perfect cube. And the problem is, if I multiply by the cube root of 2 only, I get the cube root of 4, which is not a perfect cube. So I still have a cube root in the denominator. So what I need to do is I need to multiply this not by the cube root of 2, but by the cube root of 4. Let's talk about why. And I will need to do it in the top and the bottom. Let's talk about why. If I multiply the cube root of 4 times the cube root of 2, what do I get? The cube root of 8. Is 8 a perfect cube?
Yes.
What is it? So the reason I multiply by the cube root of 4, rather than the same thing that's in the denominator, is so that I create a perfect cube. My perfect cube would be the cube root of 8. And so my final answer is 5 times the cube root of 4 over 2. If the index isn't squared, we need to multiply by a magic 1 that makes it a perfect whatever the index is. Perfect cube, perfect fourth, perfect fifth. I can do this with variables too. So ask a question now on this problem, because I don't have any more to practice yet. Tell your homework.
So just simplify 3, or index 3, 8, simplifies to 2.
Yeah, because the cube root of 8 is 2.
Okay.
2 times 2 times 2, or 2 cubed is 8.
And the 3 never changes.
Nope. Index won't change.
Okay.
Good question. Other questions on this?
If it was a fourth, you would multiply it by 8
Yep.
to get 16.
Yep. Yep. All right, let's look at Here we go. Again, sum and difference of radicals. We have to have the same index. In order to add these, we have to have the same index. But more than that, we also have to have the same radicand, or what's underneath the radical. Meaning, this part right here needs to also be the same. It is not enough for it just to have the same index. It looks weird when I just tried to highlight it. It's not enough for us to have the same index. We also have to have the same radicand. Okay? And when I add these together, this will give me a plus b times the nth root of x. A plus b times the nth root of x. Now, oftentimes we'll actually be able to add what's there. It won't always look like just a plus b in parentheses. So, for example, the first example, what is it going to be? 2 plus 3 is? Nope, this stays. It's like a variable. I don't touch what's in the radical. Once they're the same, I leave it, and I add them. 2 plus 3 is? 5. So 5 root 5x.
That's it?
That's it.
I like these.
You like these.
These ones are more money.
Now, it looks worse. It looks worse when the radicand is messy. But I'm just going to add the 5 plus the x times the cube root of 17xy. I can't add 5 and x. I don't know what those are together. Okay. That's all we can
You
do.
just leave 17 as well. Like
Can
nothing.
you simplify it? So I don't know a perfect cube of 17.
No. But so
There's-
you would have to simplify.
If you could.
But like you don't do 17xy plus or anything like that.
Nope.
Oh. Okay.
It's like variables. It's like terms.
Yeah.
You can only add what's alike.
You-
Now you know it's not going to stay this easy, right?
No.
Because it's
I
math.
can hope.
Okay. This process works even if it doesn't look like they're the same. None of these are they all have the same index. Like this is a square root, this is a square root, this is a square root. But none of the radicands are the same. Yet.
Simplified though to the same.
Let's see if simplifying these takes it down. This is 4 times 3. 12 is 4 times 3. And we know the square root of 4 is 2 root 3.
It's gonna be 25 times 3.
This is the square root of 25 times 3, which means this is 5 root 3. Oh, look at that. And this is minus root 3, which can't be simplified. So now, are all the indices and all the radicands the same? Yes. 2 plus 5, 7. Minus 1 is 6. So I have 2 plus 5 minus 1. Even though the 1's not written there, it would be 6 root 3. I am okay if you skip from this step where you had the simplified radicals down to the 6 root 3. You do not need to show the 2 plus 5 minus 1. I do not need to see that. If it helps you on your journey to getting the answer, write it.
It's not too bad.
Not too bad. All right, try the next one. Try cube root. See what you can get.
Okay.
The cube root of 250. What perfect cube goes in? 125 times 2. So this would be 5 cube root of 2. What about 54? 27. So the cube root of 27 times 2. So we would get 3 cube root of 2. And 16. What perfect cube goes in? 8. And the cube root of 8 is 2. So we get 2 cube root of 2. All addition, so 5 plus 3 plus 2 gives me 10 cube root of 2. How'd I do?
I understand. It's just like extra brain power, you know?
All right, try the last one. Because this one has a slightly different tweak to it. Try the last one.
I usually just take pictures of the slides.
Who talks fast?
Miss Price.
She does talk fast.
I had her for AP.
And loud.
Oh my gosh, she talks really loud. That kind of helps keep me awake, I feel like. She's a good teacher.
How? How would you fall asleep?
To them and do the whole lecture like screaming at them while they're sleeping.
I don't know how you fall asleep in that class. All right, here we go.
0.
I get the square root of 28 is 4 and 7, which means it's 2 root 7. Square root of 175 is 25 and 7, so 5 root 7. 63 is 9 and 7, so we get 3 root 7. So 2 minus 5 plus 3, once my radicals are all the same. 2 minus 5 is negative 3. Negative 3 plus 3 is 0. 0 root 7 is 0.
Oh my gosh.
So you don't keep the root 7?
All right, let's call it.
No.
Hey.
How'd we do? All right, your assignment is on Math Excel.